Good morning and good afternoon. Welcome to ARI's Webinar Wednesday. I'm Sri Rao, your moderator for today's webinar entitled Earth Retaining Structures, the Forgotten Infrastructure Feature. Now I'd like to introduce our presenter and my colleague, Jerry DiMaggio. Jerry DiMaggio has more than 45 years of experience in civil engineering and heavy construction. He is internationally recognized for his contributions to design, construction, forensic assessment, and dispute resolution and innovation deployment. As a senior principal engineer at Applied Research Associates, Jerry serves as a project manager and technical subject matter expert on a diverse suite of projects. He holds a Bachelor of Science and a Master of Science degree in civil engineering from Clarkson University. He's a professional engineer in several states and a certified master trainer at the National Highway Institute. He's also an ARA associate. And now I'd like to turn the program over to my colleague and friend Jerry DiMaggio, who's been waiting to speak. Jerry?
Good morning, good afternoon again. I'm hopefully going to entertain you and provide a little bit of background and education to you on earth retaining structures. Some of you who registered may be wondering about the photograph on the title slide and then also the subtitle, and I'll talk a little bit about that. I've got about 40 slides that'll cover in about 40 minutes, a little bit more perhaps. Earth retaining structure definition, and I'm going to ask you, as I often do, as I give presentations for you to read along with me. First of all, the use of the term structure is my preference. In some geographic locations, if you use the term structure and you're a geotechnical professional, you really have no right officially to work on structures. I like structure because it connotates for earth retaining elements, either retaining walls or earth retaining systems, a different degree of respect, a higher level of respect, both in terms of design and construction. Now, at the bottom of this slide, for an elevator speech, if you're speaking to some layperson relative to definition of ERS, it's a tool that we use as a space management tool in our toolbox to make the most out of any particular site that we have based on the infrastructure facility we want to work with. Its applications of ERS, earth retaining structure, use the short handle as we go along here, are numerous. And if you look at the bulleted list that are on here, they extend way beyond highways, railways, all types of physical infrastructure we have a need for use of both temporary and permanent applications of earth retaining systems. And they're enormous, and I say they're forgotten, not so much by the geotechnical community, but by the other disciplines that we work with. It's not given the same respect, as an example, in the highway arena as a bridge or the network of pavements that we have. But earth retaining structures can play a very significant role, not only in the application of development of the infrastructure features, but more so allow us to do many things that otherwise would not be possible with many of the sites that we have to deal with today. Like a lot of things in life, we've got lots of choices when it comes to earth retaining structures, and they're listed here. I'll talk a little bit briefly about how we can break these down into categories just momentarily. At the conclusion of today's webinar, I'll give you a little bit of insight into a process that was developed by some colleagues of mine over 20 years ago to use a rational process on how do you select the technically appropriate and the most cost-effective earth retaining system that you have based on the project criteria, constraints, and the requirements that we have. More about that to come. So similar to what you find in a grocery store as we look for toothpaste or we look for cereals, we've got so many choices that we're sometimes befuddled in terms of what's the right choice, because I don't want to make the wrong choice. And in this case, if you're like myself, you might get yelled at if you bring the wrong cereal back home. In this case, with a retaining structure, if you select the wrong earth retaining structure, it'll be worse than getting yelled at. So let's look a little further in terms of what's available to us. We can classify walls by several different methods. Scientists and engineers love to classify things for a variety of different reasons, but we can get into that on a different topic discussion on a future webinar perhaps. They fall into three categories, these classifications. The load support mechanism, we'll talk momentarily about each of these, the construction method, and the earth retaining system rigidity. Now, let's first take a look at classification by load support mechanism. And we can classify them into one of three categories under load support mechanism. Externally stabilized walls, these where loads are supported, that is, loads that are applied to the wall, are supported by some kind of an external structure. Internally stabilized walls, these are loads that are supported by some form of soil reinforcement interaction. In the third category, and it's not because we can't make up our mind, as I mentioned just momentarily, are hybrid systems. And these are sections that we often run into where a combination of wall types are appropriate based on the constraints and the requirements that we'll get into at the conclusion of today's webinar. Now, if we look at these, first of all, in a schematic form, the externally stabilized systems, a few of them are shown on this slide, and then I'll show you photographs momentarily. They fall into a large category of earth retaining systems, as you can see here. Some examples, we have a countersort wall in this slide, slide 12, shown on the left. Slide numbers, of course, are shown in the lower right-hand corner of this presentation. On the right, under certain circumstances, we can use, such as shown here, a strutted system, that's an earth retaining system, or a raker system, which is not shown. We have a variety of crib and bin walls. This is an open face bin wall that's shown on the left, or a chia wall, sometimes people refer to it, because after the vegetation is fully developed, you won't know that there's a retaining structure present. On the right, another externally stabilized system is a ground anchor system. This is a permanent ground anchor solution that's being employed for the stabilization of some landslide that's unfortunately occurred at this particular site. So the second category are internally stabilized systems. On the schematic on the left, the mechanically stabilized earth, and the schematic on the right are soil nailing. And these systems, and I said I'd tell you a little bit about the introductory photograph. That's obviously not a retaining structure. It's a religious temple in Mesopotamia, some part of Iraq these days as we commonly know it. And that structure was constructed to a height of about 260 feet. It was constructed not as an earth retaining structure, but a temple by humans that resided in that particular location to become closer to God. And it was thought that God would be in the sky. And if you were human, you wanted to get closer to God, so you raised the elevation that you were at. What's the pertinence relative to today's slide? Well, that system is a historical form of mechanically stabilized earth. And today, in these systems that we see in internal reinforcement, we use buried steel, we use some kind of a polymetric reinforcement. None of those existed, obviously, thousands of years ago. The concept of reinforced soil was born, however, with the use of branches and reeds. And that structure of the photograph that you saw is thousands of years old. So now when we talk about design life and service life for infrastructure facilities, our forefathers and foremothers had us beat by thousands of years. Some photographs of those internally stabilized systems. On the left is a mechanically stabilized earth wall abutment. On the right is a permanent soil nail wall structure under construction. Classification by construction methods. Some walls are built from the bottom up. Those are fill walls. Some walls are built from the top down, and those are cut walls, bottom construction. Now, what's significant to make a comment about related to construction procedures is the fact that the design protocols, which are well formed for generally all of the retaining wall systems that we commonly use today in our practice in both temporary and permanent applications, are predicated on the means and methods and the technique of construction. So if we use, by some wild and crazy scheme, some different means and methods to construct either a fill wall or a cut wall or a hybrid wall, we have to scratch our head and think whether we've compromised the legitimacy of using the design protocols that have been developed in association with that means and methods of construction. Very important thought. So some example of bottom-up walls, and you probably guessed these, you know them by heart. Most prevalent of these is mechanically stabilized earth walls. They're most commonly used fill wall in the United States and perhaps worldwide for a variety of reasons. And then if we look at cut wall systems, we got many other choices. Again, these are commonplace systems in today's practice for both temporary and permanent applications. Finally, the classification by system rigidity. And this is the least of the three classification methods that most engineers ever think of, and they fall into two categories: rigid walls and flexible walls. And most of the walls that we use in practice for both temporary and permanent applications are flexible. And that flexibility assists us in allowing the soil, and in some cases the rock, to mobilize its inherent strength so that the result is such that the moments and the forces that are applied at the actual retaining structure face are less than if they are a rigid wall. Now, that doesn't mean that we can always use a flexible wall. In some cases, a rigid wall is appropriate. That, again, is a further discussion that I don't have time for today. Now, I've already mentioned temporary and permanent walls. And the definition might be slightly different based on the area of infrastructure that you work in. Relative to AASHTO, for example, as you can see, for temporary walls, we typically think of a temporary structure having a service life or a performance period that's required of 36 months or less. Having said that, many of the major highway infrastructure projects that are undertaken in the U.S. might extend to have a construction life of 5 or 6 years, but yet they're only temporary structures. Supportive excavation systems, some people might suggest that we can use for temporary applications and these applications less restrictive design requirements, but these temporary applications, depending on the constraints and the specifics of the project, can be just as severe in terms of the consequences of poor performance as a permanent wall failure, whether it be for serviceability or a total collapse. Permanent walls, generally in the highway application industry, the design life or service life of retaining structures that are permanent are 75 to 100 years. In some cases, as we already mentioned historically, the actual performance might exceed 100 years. In industrial applications, it might be less than 75 years, more typically, in some cases, as low as 20 years for commercial industrial applications. It depends. The distinction between permanent and temporary are probably in most applications outlined by material durability. We might, in some cases, for temporary applications, use lower resistance factors. We might design them for lower loads. The performance expectations might be slightly different. And overall, from an appearance and aesthetics point of view, temporary walls are very different in many cases than permanent walls. Now, I want to speak a little bit about subsurface exploration programs because the poor performance of earth retaining structures, which unfortunately occurs more often than we'd like it to occur, either during construction or in post-construction, is not related to the design protocols that we use. It's often related to an improper selection of the geotechnical parameters that are necessary to design and to construct the wall. And this begins with the subsurface exploration program. Now, many of you who are joining us today on this webinar are not geotechnical specialists. So without taking a deep dive and really taking a superficial dive in this area, let's talk a little bit about the expectations that we have when a geotechnical specialist undertakes a subsurface exploration programs. The expectation of what we're trying to uncover are those that are listed here in the bullets. We, of course, want to know what the subsurface conditions are at the site. We're going to take some samples. We'll talk a little bit about that. Often forgotten is the importance of groundwater conditions and the variability of groundwater. The variability across the site, both horizontally and vertically, and finally, whether or not there are some potential geohazards that could impact the performance of our earth retaining structure. Now, in private practice, I know many of you work in private practice, or at least work on some private projects. We might undertake a major retaining structure and not have any explorations. This is pretty foolish, in my view, and should never be done. And if your owner resists you taking what I would and you might consider an adequate exploration program, first thing you do when you look in the mirror tomorrow morning is to say, have I done as good a job to demonstrate to the owner of the value added and the return on investment for undertaking an adequate subsurface characterization program? Let's look a little further at this in terms of what I mean by an adequate exploration program. What we see in slide 22 is we're briefly looking at a plan and a profile view, and we could argue a bit or have a healthy discussion in terms of the plan view and the distribution of the explorations. And we say explorations here because they can be done by a variety of means, not only drilling and sampling, but can be done by things such as the cone penetrometer, either dynamic or static. You turn our attention to the section view. Those of you who are not geotechnical specialists might ask the question of, yeah, I understand why we take explorations at the wall line, but why do I need an exploration in back of the wall and in front of the wall? Well, this is for a variety of purposes. One of the checks that we should be undertaking is the potential for global stability. One of the areas that global stability is going to be affected by the geotechnical materials in front of the wall and behind the wall. As we looked briefly before, some of the wall types require us to install things like permanent anchors or soil nails. These are cut wall applications. So we want to know, unlike in a fill wall application, what materials are going to be encountered some distance that can be accurately estimated and calculated behind the actual wall face. We don't want to be surprised during the actual construction. So we take generally some type of samples. I don't have a slide because of time constraints, but if we don't take samples, we would take some frequency of sampling that would either be disturbed or undisturbed, as shown here, but we might also use in situ testing methods. But what is the outcome of this that's beyond the actual drilling holes, squashing samples, collecting samples? What we want to know are the engineering properties of the geomaterials that are going to be impacted by the presence of the wall and in turn are going to be impacting the wall. Now, I mentioned groundwater. Groundwater is an elusive character and is often, unfortunately, a primary cause of some of the problems that we have during construction or in post-construction with earth retaining structures. And I'd ask you to just scan read the bullets that are listed here, because the presence of subsurface water, and later on I'll speak in terms of drainage and surface water, has a tremendous impact on the geomaterials and hence has a tremendous impact on the performance of our earth retaining structure for that long service life, whether it be temporary or permanent that we spoke a little bit about before. Now, when we deal with earth retaining structures, we have to talk a little bit about the loads. And the loads are generated from several different types of sources, lateral earth pressures being one that's obviously generated by the material which is behind the wall. And the relationship of lateral earth pressure to vertical earth pressure depends on the basic equation that you see here, and I've gotten definitions for that value. P sub H is the pressure at a given depth horizontally, and that is equal to some coefficient of earth pressure, K, times the vertical earth pressure at that depth. So the horizontal pressure and the vertical pressure have a direct relationship to each other. And K is the elusive value here Most of you are familiar with the terms the at-rest earth pressure condition, K0, the active earth pressure condition, Ka, and the passive earth pressure condition, Kp. Where the bugaboo comes in, and often what's misunderstood in practice, and unfortunately relates to some performance issues on some projects. I don't want to give you the impression that many retaining walls fail or have poor performance. The vast majority, by far, perform excellent during their entire service life. But back to the limit states of active, passive, and at rest. A design decision by the designer at a given project time is to decide what condition of earth pressure needs to be applied for the design. And there's a significant variation in the difference between a Ka value, which is the lowest pressure, compared to a Kb value. And some people use a simplistic approach, and we'll look at a simplistic approach in a minute here. 3 different types of lateral earth pressure are usually considered. What's often forgotten is not the issue of whether the wall moves away from the soil, such as depicted by the schematic on the left, or the wall moves into the soil or the geomaterial as depicted by the schematic on the right. Those are very important, of course, but we also have to consider the application and the sequence of construction relative to the feature. So, for example, if we're in a bridge and we're at an abutment, and we're looking at that abutment construction, we should be considering the type of abutment that we have. An abutment, by the way, is just an application of an earth retaining structure. How that abutment design is tied to the superstructure. So those 2 variables would dictate to me whether or not I could use Ka or I could use K0. In many cases, the appropriate term to be using would be K0 for the example that I just gave. In many cases, however, Ka would be appropriate. Now, what about Ka and Kp? And we look at this as a little schematic to illustrate what I was showing very simplistically in the previous slide. And we look at movement, and for the non-geotechnical specialist, we don't want to give an incorrect impression of movement, because the amount of movement that it takes to develop the active earth pressure condition is about 1/10 of the movement that it takes to fully mobilize the passive zone of resistance. Now, for fill walls, generally we ignore the benefits of embedment for routine embedments of, let's say, 2 to 3 feet for a variety of reasons. But for cut walls, we depend on that passive resistance and the mobilization of that passive resistance to allow us to develop the full structural strength, the bending resistance for cut wall applications. Now, the difficulty in a cut wall application relative to passive resistance is to take a close look at the amount of deformation that it takes to fully mobilize the passive zone of resistance, and that amount of deformation is roughly an order of magnitude greater than it takes to mobilize the active state of earth pressure. Now, when we're all said and done, the other factor that we have to look at is what's the influence of water, and we'll get to where's our friend water again, and water, as we talked about, can create a bit of a problem for us. Why is water so elusive? Well, before we get into that, we'll talk more about that in a bit. But water is a problem because water has no shear strength. And as compared to typical soils, since water has no shear strength, then the vertical stress as a function of depth behind the wall is going to be the same as the horizontal stress that's applied laterally to the back of the wall. The water weighs, as we know, 62.4 pounds per cubic foot. That means for every depth foot of water, I have an increase of pressure of 62.4 pounds vertically and horizontally. That's roughly about 3 times what we would get in a fill wall situation when we use the granular backfill. So designing water pressures. I already mentioned the first bullet. Some other considerations, depending on application, is to consider groundwater drawdown, during the life of the structure. Consider the permeability of the walls. Some of the walls that we talked about at the beginning of the webinar are permeable. That means they allow water to pass through, and some walls are watertight. The selection of the wall in certain applications, if we're in a location such as Washington, D.C., such as Boston, such as New York, and many other locations, then it's very important that we select the wall to be in concert and complementary with the existing groundwater conditions that exist at this site before we build our new infrastructure feature, which is going to include either a temporary or a permanent retaining wall. For if we compromise that existing water regime, then we may be adversely affecting the structures that are nearby. Now look at the last bullet. Many failures are caused by poor drainage, high groundwater pressures greater than what are considered in design, and higher groundwater pressures that exist in the in situ condition but are modified by the actual construction of the infrastructure facility. The third area, we talked about earth pressures, we talked about water loads. Third area of loading is surface surcharging. The magnitude of surcharge really depends on three variables. One is the geometry, and those geometries are listed here by, I've got them listed by type. Second is the intensity of the stress that's applied to the application of the surcharge load. And third is the location of the surcharge load relative to the face of the wall. And if you just can visualize for a minute that I can get to a certain offset distance at the top of my wall where I can apply an enormous surcharge, but no stress horizontally will reach any point along that vertical wall surface. Now, up to now, I've introduced you to the three areas which introduce loads and moments to the wall, and I also briefly mentioned, although I didn't refer to them as theoretical earth pressure diagrams, that's active, that's passive, and that's at rest. For certain wall applications, and the best example is a ground anchor wall, we use what are called semi-empirical earth pressure diagrams, and rather than having a triangular distribution such as I showed you previously, we have a trapezoidal distribution depending on the number of the external sources. This would be an earth pressure distribution that you would also see in concert with a raker system or a strutted system, at least as far as the horizontal components that are applied, certainly most prevalent for a ground anchor system. So we have two types of earth pressures that we can use: triangular distributions based on theory and semi-empirical earth pressure diagrams. And everybody knows, I'm sure you forgot, some of you, semi-empirical means that it has a theoretical basis, but it's validated based on ground truth. And the envelopes that you see here, for example, which are for cohesionless soils with ground anchor applications based on a large variety of instrumentation programs, envelope all of the data relative to the magnitude of the pressures on those 20, 30, 50 different case histories. That means that at a particular location, as long as you have the conditions that go along with the footnotes in these diagrams, which I'm not showing, you will end up with pressures at the back of your wall are far less, or less than certainly what are estimated by these equations that you see here. So if you're astute and you have a large project, you may go out to a site, you might put in a modest instrumentation program and come with a much more efficient design, not an optimized design per se, for your earth retaining structure envelope in terms of pressures as a function of depth. Now, let's talk a little bit about water for a minute. Surface runoff. Surface runoff is going to be a consideration that often on projects gives us problems, but it gives us problems because it's almost like no one's responsibility. So the consideration of drainage, which includes subsurface drainage as well as surface runoff as shown in this slide, has to be specifically defined for each and every project because it's going to vary by each and every project. And when we look at subsurface drainage systems, so we're worried about surface runoff, as we said just a moment ago in design, and subsurface drainage, often we put what is often referred to on the left A chimney drain that might consist of drainage aggregates, such as I've shown on the schematic on the left, or more often than not, might be a geocomposite system, which is a compilation of more than one geosynthetic products to form a cuspated drainage system to collect water and carry it away from the back of the wall. Unfortunately, the drain that you see on the left actually, in many cases, exacerbates the magnitude of the water pressures that are introduced to the back of the wall. And depending on the site conditions that we have, a schematic which includes a drain at the base of the wall or an incline drain that extends beyond the select fill in a fill wall or extends some distance beyond the theoretical earth pressure, theoretical failure plane that is immediately behind the wall and collects the water before it reaches, even in a reduced fashion, the back of the wall. The drain on the right is a more appropriate drain. So it's not as simple as the moral to this story, and we could talk quite a bit about this topic, but we don't have time, is that a simple chimney drain, as shown on the left, may cause more problems than solve a problem, in spite of what you think that you do to the development of the pressures, water pressures at the back of the wall. Well, we're back where we started, and I promised that I would speak to you a little bit about how do you select the right type of cereal, and for that matter, it could be toothpaste. The same thing applies. You go to the grocery store, you don't have two types of toothpaste. You have 102 different types of toothpaste. And now we've got all these retaining walls. You have a project. There's got to be some kind of a rational approach that one can look at to select the right type of wall. And that's what we want to do in the next few slides. This wall selection flowchart was developed, as I mentioned at the beginning of today's webinar, by a few colleagues of mine who are still in practice. It was developed for Federal Highway Administration Circular number 2, which was one of the early geotechnical engineering circulars. You probably could still obtain a copy. It's been resurrected again in a new National Highway Institute course that I've had the honor and privilege to update with one of my two colleagues that developed this particular system. So let's look at the system briefly in a few minutes that we've got remaining. First of all, identify a need for an earth retaining system, right? We do that. That sounds a bit foolish, but earth retaining systems cost money. They vary in terms of cost over 2 orders of magnitude from the least expensive system to the most expensive system. And although we build in the United States over 100 million square foot of earth retaining system every single year on infrastructure facilities, we don't want to use them unless we have to. Step 2. Identify the constraints and the project requirements. We're going to look a little further into each of these steps as we go along. Step 3, evaluate the project requirements against the factors affecting wall selection. Now, that's not a design. That's just looking at it from a consideration as, not even a preliminary design, but a consideration of factors that we'll look at momentarily. Then Step 4, evaluate all alternatives against the wall selection factor. And finally, Step 5, select acceptable wall type or types. And often in many applications, you may find that from a technical point of view, and that's what we're talking about in steps 1 through 5, is to identify, first of all, what technical wall, from a technical perspective, what wall types meet all of the criteria that are appropriate for a project. So, identify the need, and if you don't use a slope, if you don't use a wall, maybe a stable slope or a reinforced soil slope might fit the bill, fit within the right of way and meet the performance requirements of the project. Step 2, identify the site constraints and the project requirements. Well, what do I mean by that? And you see those items are listed here. Limited right of way or headroom, what area is available for on-site material storage, access to construction equipment, utilities, and nearby structures that have to be considered based on the particular project considerations, aesthetic requirements, and we've come a long way in terms of aesthetics within reason for whatever the owners or the external stakeholders desire. At a minimal increase in cost, we can pretty much address any aesthetic requirement as long as it doesn't get too wild and crazy, then it may have an adverse effect on cost. Environmental issues, expected wall height. Now, some walls can be built to very high heights. For example, mechanically stabilized earth walls in the United States. I believe the highest one is at a runway for the Seattle-Tacoma Airport, approximately 140 feet high. So you might ask yourself, can all walls be built to 140 feet height? I guess theoretically, but economically and practically, each wall has got some limitations, both in terms of cost and in terms of technical feasibility. Wall selection factors. Well, what do we mean by this? Wall selection factors, they would include some of the items that we see here. What kind of ground do we have? Talk quite a bit about water, and I did that intentionally in this webinar because water can cause you lots of headaches and lots of problems if you don't give due respect to both the surface water impacts and the subsurface water impacts on your retaining structure. Construction considerations. It depends on where we're at. Not all of the tools and the construction equipment that are needed for certain types of walls are readily available in some locations. Speed of construction. We have the need for speed today. We know that, to use that from a movie statement, but the speed of construction often is a driving force in the selection of certain wall types on certain projects. Right away, of course, again, we're talking about a space management tool. We already talked about aesthetics. Environmental concerns, apologize for the faux pas on the slide. Durability and maintenance. Durability. Whenever we put any material beneath the ground, we have to give due respect relative to the performance and service life that's required for the feature, not only retaining walls, relative to the considerations of corrosion or other mechanisms of deterioration. Concrete can deteriorate, obviously not by corrosion, although the reinforcement of concrete can, of course, corrode, but concrete itself as a material can undergo deterioration. Polymers can undergo deterioration. Tradition. I've never built a certain type of retaining wall under my watch, and I'm really uncomfortable with it being used while I'm on watch. I don't care if it was done by the state next door. I don't care if they built 1,000 of these. I'm really uncomfortable, and somebody's going to have to hold my hand and make me feel comfortable before I use that particular new system on my projects. Contracting practice, and finally cost. So we look at all the technical aspects, and we look at how do we get some realistic information. And again, I want to draw your attention to GEC2 and not released yet, but the new FHWA updated course on earth retaining structures provided through a National Highway Institute. Now for fill walls, and this is an updated version of what was in GEC2, we have, let me just crosswalk you across these two tables. There'll be one for fill walls and one which will immediately follow for cut walls. We've got listed here most of the prominent type fill walls by wall type, whether they're applicable to permanent or temporary applications. What's a cost-effective height range? And this is kind of, there's exceptions, of course, to the minimum and the maximum. What's the required right-of-way, roughly? And that, of course, is going to give you some ranges that can be exceeded. Differential settlement tolerance. Now, this bears a quick explanation. In terms of differential settlement, what we mean is performance without the stress to the particular type of wall along its alignment. Now, all walls are used in a variety of applications. I mentioned abutment earlier on in the presentation. So just because a concrete cantilever wall has a maximum tolerable deformation of 1 in 500, that means 1 foot differential in 500-foot length of wall, that might be far in excess of what's considered to be tolerable deformation for a particular abutment application, in fact, all abutment applications. Finally, the two other headers, what are the advantages of each respective wall type and the limitations? Now, as Shree's going to remind you in a moment or so, you can get a PDF version of today's presentation if you already haven't downloaded it. It'll be readily available to you, so you can look at these at your leisure and use them for your future applications. So what we just saw for fill walls, we have a companion table for cut walls. Those are listed here, just a few of them that are listed here, but the same concept. One other heading, excuse me, two other headings that we didn't see for fill walls, because fill walls generally undergo very little movement because they're used predominantly in flexible wall applications. The two other headers that we didn't see for fill walls were lateral movements and water tightness. So I wanted to make sure that called you that to your attention. Final slide, getting back to our selection criteria, we've got an example of and it's irrelevant what this example is for. So for each of the conditions that we have, the variables that we mentioned, the groundwater, the construction considerations, speed of construction, etc., and finally cost, we've given you some guidance relative to cost and some of these other details in the previous tables. The other variables are going to be dictated by a particular project. Likewise, the owner's weighted rating is going to be determined by the owner or the owner's design engineer on a particular project. And you can see those ratings vary from a value of 1 to 3, depending on the particular project. And then for wall types that have been at a preliminary assessment, wall types are listed, several wall types were considered, and they were rated based on that value of 1 through 4, based on ground conditions. So for example, a reinforced soil wall for the particular project that we had a rating of 2. A geotextile wall for the particular project based on the ground conditions. The ground conditions, of course, are project specific, had a value of 3. And if you look just by inspection, the purpose of this slide is just to show an example of the results. And what we end up with is the wall types that have, as a result of this exercise, the highest values are going to be the wall types that really are attractive for the particular application. So that is the conclusion of my presentation, and I'd like to turn the program back over to my good friend, Dr. Sri Rao.
Thank you, Jerry. That was a very informative presentation, and I learned a lot through your presentation. To the participants on the webinar, you may now begin submitting your questions in the Q&A pod, and Jerry will answer as many questions as possible in the time that is remaining. The upcoming webinars, here's some of the upcoming webinars, and we hope you enjoyed today's webinar, and you'll join us for some of our upcoming future webinars. 3 of them are listed on the screen. On June 28, 2023, Stephen Kirkpatrick will talk about research supporting safe transportation of hazardous materials by rail, a very timely topic for the next webinar. And then in July, on July 19, Timothy Parsons will talk about Pave Air, FAA's free pavement management software. And then on August 16, we have another geotechnical topic, knowledge-guided machine learning for geotechnical resilience by Dr. Ahmad Al-Hassan. So we'll get to the Q&A portion. There's a few questions, Jerry, if you wouldn't mind answering. Charles is asking, if water is so critical to earth-retaining structures' performance, why is it so difficult to properly address water?
So that's a very good question, Charles. And I'll give you my elevator speech answer to that is, and the key factor is water is changeable, and water changes during the life of a structure. Water changes in terms of the water regime during the as a result of the construction of the earth retaining structure. And third factor is that water is a very complex regime. So we think in terms of water as an underground river or a stream. That's probably the wrong visualization in many cases. So it's very difficult to categorize. As Sri will mention, if you have follow-up questions, I'd be happy to, if you send me an email, be happy to further elaborate on that topic.
All right, thank you, Jerry. Here's a question from Randall. Is there a commercial software you prefer to use for earth retaining structures global stability modeling?
I have my own thank you for the call. There's several. I have my own preferences, but I prefer not to identify them by commercial name. I don't believe that would be appropriate. But you have more than a single choice for looking at global stability that can allow you to, in some cases, incorporate reinforcements, incorporate external forces such as ground anchors. But they're easy to find, and I think they're generally reasonable as software costs are today. Sorry, I can't be more specific, but I don't think that's appropriate for me to respond with a commercial name.
Understood, Jerry. Here's another question, and this one is from Aiden. What types of surface and subsurface defects are more common on MSC walls?
Was that defects? I'm sorry.
That's correct, defects. Let me repeat the question. What type of surface and subsurface defects are more common on MSC walls?
Well, let me begin by saying that the existing protocols that we use for mechanically stabilized earth walls, and for that matter, reinforced soil slopes, they're immature, and I don't think anybody listening here should have any reluctance to use them with confidence. When we do see defects, either during construction or in post-construction, they're caused by people not following the rules of design or construction. There might be the stress that's seen in the panels or the joints, closure joints. There might be deflections that we see in terms of panels over time. It might be cracks in panels, cracks in coping. It might be depressions at the surface or below the bottom of the wall. It might be, in some cases, unfortunately, a total collapse of the structure, and this can occur both in terms of during construction and in terms of post-construction. But I personally have the utmost confidence if you follow the rules, you'll stay out of trouble.
All right, thank you, Jerry. The next question is from Mesdine. I'm not entirely sure what this question is asking, but maybe you might be able to answer. Do you have any idea about the inspection of corrosion occurs on the linked reinforcement rebars embedded in MSC wall? If you wouldn't mind, Jerry, talking about the inspection of corrosion in terms of for the rebars embedded in MSC wall, that would be helpful.
Well, I think measuring corrosion overall of underground metallic systems is very difficult, and the prediction of rates of corrosion is a very difficult process. If we're talking about long-term evaluation of corrosion rates in elements such as nails or ground anchors, but the particular questions for MSC walls, metallic reinforcement, then I believe the most successful technique that's been used over time with some degree of accuracy is linear polarization resistance. And I personally used that on several projects with a fair amount of success. But when you look at measuring corrosion, you can't do it at a one-time evaluation because the rates of corrosion vary over time, both in terms of the months of the year, the weather environment, and certainly over the life of the embedded metallic element.
I think there's a follow-up. Missy says, which are anchors, not rebars. Does the answer change there if it's anchors rather than rebars?
No, because, I mean, It depends on the level of corrosion protection system in the anchor. I mean, you know, if it's a ground anchor, then when I think of ground anchors, I use the term twice. I'm thinking about a drilled and grouted anchor, not a helical anchor, not that there's anything wrong with helical anchors, or a dead man anchor. So I'm talking in terms of a grouted anchor. A grouted anchor can either be a tendon, which is a rebar, which can be solid or a hollow, or it can be a strand. So it really doesn't matter what the metal is. You need access to the metal, so it doesn't really vary. Some people have tried real quickly with embedding coupons, short lengths of reinforcement, in particular for that can be extracted over a duration after following construction, 1 year, 5 years, 10 years. The problem is with doing that, you get a false reading of what the true rate of corrosion is, because it doesn't fully replicate the variation of the potential along the length of the anchor or the mechanically stabilized earth element or the soil nail. It really gives you, it's not the same environment at the face of the wall, and you have to look at the entire length of the reinforcement to get the true picture of the rate of corrosion.
Thank you, Jerry. Here's a question/request. You didn't talk about seismic. Could you address best wall types for high seismic loading conditions?
Yes, and I'll do two things. First of all, to point you to a reference, and there might be more than I'm familiar with, but those of you who are not familiar with the AASHTO Bridge Design Codes, the latest edition is April 2020. It might be a new edition pending. Look at Section 11 that deals with retaining structures and abutments, and look at Appendix A of Appendix 11. Look at Section 11, Appendix A, for seismic design for earth retaining structures. The two best performing walls, after being unfortunately exposed to multiple seismic events worldwide, are soil nail structures for cut and mechanically stabilized earth structures for fill. And in both cases, that's due to their flexibility. They do undergo, in those high seismic events, they do experience some magnitude of permanent displacement, but generally they would not experience a catastrophic failure as you would see with other types of retaining walls.
All right, thank you, Jerry. Now here's a question that I personally am interested in also. I see MSC walls everywhere. Why do you think MSC walls are so popular?
Well, that's a good question. I use a cliche, and certainly Florida doesn't have a monopoly on this market. But if I throw a rock in Florida in any direction, I hit an MSC wall and a geotechnical engineer. I think I'm guaranteed to that. But anyway, to answer the question, they're most common because they're relatively simple to construct. Their design protocol has been proven to be valid when the rules are followed. Remember, the first MSC wall constructed in the United States was built in 1972 in Los Angeles, so they've been around for a while. Inexpensive to construct and simple to construct, and also have a lot of latitude relative to aesthetics, and then flexibility of variations of geometry around a site.
Thank you, Jerry. I think that's all the time we have for this Q&A. Thank you, everyone, for your responses. We have just a few more minutes, and if we did not get to your question, Jerry has agreed to answer questions for the next 24 hours via email. We just ask that you please make sure your questions are not consulting questions, and please understand that the sensitivity of the topic may limit his ability to respond, such as the software type and things like that. Jerry may not directly respond to what his favorite software is for designing walls. But Jerry's email address is shown down on the screen, and you can email him directly if you have any questions. ARA is a great company to work for, and it's growing, and we are always looking for more great people to join our team. If you are interested in employment opportunities with ARA's transportation and infrastructure offices, please send a brief resume and contact information to www.joinara@ara.com. That's WW stands for Webinar Wednesday, so www.joinara@ara.com. Thank you for joining today, and we hope you will join us in a couple of weeks on June 28th, almost a month away from now, for our next webinar Wednesday, Research Supporting Safe Transportation of Hazardous Materials by Rail, and that presentation is by Dr. Stephen Kirkpatrick. Thank you for joining, and have a great afternoon.